This video is for those of you who might be going back to school and taking a calculus course. In this lesson, we're going to focus on three fundamental concepts in calc: limits, derivatives, and integration. Let's start with limits. So let's say we have some function f of x, and it's equal to x squared minus 4 over x minus 2. What is the limit as x approaches 2 of that function? So what exactly is a limit? What does it do? So basically what this question is asking is, as x approaches 2, what does the y value, or what does f of x approach? Now, one of the first things you could try is direct substitution. If we plug in 2 into the function, it's going to be 2 squared minus 4 over 2 minus 2. 2 squared is 4. 4 minus 4 is 0, and 2 minus 2 is 0. 0 divided by 0 is undefined, so that won't help us. So what we can do instead is we can plug in a number that is very close to 2. Let's try 1.9. So let's find the value of f of 1.9. So that's going to be 1.9 squared minus 4 over 1.9 minus 2. (1.9 squared minus 4), that's negative 0.39. 1.9 minus 2 is negative 0.1. When you divide these two, you're going to get positive 3.9. Now what if we plug in a number that's even closer to 2? So let's say 1.99. What's going to happen? Well, let's see what we're going to get. So 1.99 squared minus 4, that's negative 0.0399. And 1.9, this is supposed to be a 2, by the way, not a 4. So let me just fix that. 1.99 minus 2, that's equal to negative 0.01. And so let's divide these two numbers. And this is equal to 3.99. So here's a question for you. As x gets closer to 2, what happens to the y value, or basically the value of the function? Notice that it gets closer and closer to 4. 3.99 is a lot closer to 4 than 3.9 is. So therefore, we can make the conclusion that the limit as x approaches 2, as we get closer and closer to 2, the value of this function approaches 4. And so this direct substitution technique can always work. If you can't plug in the number directly, you can plug in a number that's very close to this number. And as you'll see, the limit approaches a certain value. Now let's go back to the first problem. It turns out that there's another way in which we could get the same answer. So even though we can't plug in 2 directly because it's going to be undefined, we can simplify the expression. We can factor x squared minus 4. And it's a difference of perfect squares, so it's going to be x plus 2 times x minus 2. So notice that we can cancel a factor. We could cancel x minus 2. And so what we have now is the limit as x approaches 2 of x plus 2. At this point, we can use direct substitution. We're no longer going to have an undefined value. So if we replace x with 2, it's going to be 2 plus 2, which is equal to 4, which confirms our previous answer. So sometimes there are certain algebraic techniques that you can use to evaluate this limit other than using direct substitution with numbers that approaches 2. Now that technique always works, so it's a good fallback method. But on a test, you may have to show your work, so you need to also learn the analytical methods with it as well. So I'm going to give you 4 problems, and I want you to evaluate the limit. So let's start with this one. what is the limit as x approaches 3 of x squared plus 5x minus 4? Feel free to pause the video and work on this example. Now in this problem, we could use direct substitution. If we plug in 3, we're not going to get an undefined value. We're not going to get a 0 in the denominator of a fraction. So always check to see if direct substitution will work. So this is going to be 3 squared plus 5 times 3 minus 4. 3 squared is 9, 5 times 3 is 15, and 15 minus 4 is 11. 9 plus 11 is 20. And so this is the answer for this example. Now what about this one? What is the limit as x approaches 3 of x squared minus 8x plus 15 divided by x minus 3? Now if we try to use direct substitution, if we plug in 3 minus 3 is going to give us a 0 in the bottom of the fraction, which will make it undefined. So therefore we don't want to do that. Let's see if we could factor the trinomial on top. So what two numbers multiply to 15 but add to negative 8? So we know that 3 times 5 is 15. But we need it to add up to negative 8. So we need to use negative 3 and negative 5. So therefore, x squared minus 8x plus 15 is equal to x minus 3 times x minus 5. And now, we can cancel x minus 3. So we're left with the limit as x approaches 3 of x minus 5. By the way, some teachers will require you that they want you to rewrite the limit expression until you replace x with 3. Some teachers will take off points if you don't rewrite the limit expression. So I just want to give you that warning so you don't lose points on a test. So now let's plug in 3. So it's going to be 3 minus 5. At this point, we don't need to rewrite the limit. And this is equal to negative 2. And this is the answer. Now what about this one? What is the limit as x approaches 4, given a complex fraction 1 over x minus 1 over 4 divided by x minus 4? Now in this case, we can't factor. There's nothing to factor in this example. But whenever you have a complex fraction, here's my recommendation. Multiply the top and the bottom by the common denominator of the smaller fractions that you see. So in this case, let's multiply the top portion of the fraction by 4x and the bottom by 4x. On top, let's distribute 4x times 1 over x. The x variables will cancel, leaving behind 4. And don't forget to rewrite the limit expression. So this is positive 4. And then if we multiply 4x by 1 over 4, this time the 4's will cancel, leaving behind negative x. On the bottom, you don't need to change anything. Don't distribute the 4x, just leave it the way it is. Notice that 4 minus x and x minus 4 are very similar. They're not exactly the same at this point, but there's something that we can do in the next step. Let's take out a negative 1 from 4 minus x. Let's factor it out. If we factor out a negative 1, negative x changes to positive x, and positive 4 will change to negative 4. So notice that now we can cancel x minus 4. So we're left with the limit as x approaches 4 of negative 1 divided by 4x. Now we could substitute x with 4, and we don't need to rewrite the limit expression at this point. So it's negative 1 divided by 4 times 4, and so the answer is negative 1 over 16. So this is it. Now let's confirm that negative 1 over 16 is indeed the answer to this problem. So if you're not sure, you can always plug in a number that's close to 4. You can't plug in 4 directly because 4 minus 4 is 0. But let's plug in a number that's close to 4. Let's use 4.1 and then let's use 4.01. So let's find the value of f of 4.1. So that's 1 over 4.1 minus 1 over 4 divided by 4.1 minus 4. Now 1 over 4.1 minus 1/4. That's equal to negative 0.0060975. And there's a 6 after that. 4.1 minus 4 is just 0.1. And so this gives you negative 0.0609756. So let's keep this value for now. Now let's try f of 4.01. So that's 1 over 4.01 minus 1/4 over 4.01 minus 4. So the numerator has a value of negative 0.0006234. And the denominator is going to be 0.01. So I'm going to put this value up top since I'm out of space on the bottom. So this is about negative 0.0623. Now let's say if we want to go further, if we want to try f of 4.001. I'm not going to write it out, I'm just going to type it in the calculator. So this is going to be negative 0.06248. So notice that it's convergent to a certain value. Here it was negative 0.0609. Here it's negative 0.0623. And now it's negative 0.0624. And I'm missing a 0. It's supposed to be a 0 somewhere here. So it's convergent to a certain value, which means that the limit exists. Now, negative 1 over 16, if you type this in your calculator and convert it to a decimal, this is negative 0.0625. As you can see, these two answers are very close, even though they're not exact. But as x approaches to 4, as it gets closer and closer to 4, this value is convergent to negative 1 over 16, or negative 0.0625. I keep forgetting the 0, but that's supposed to be 0.0625. Let's try one more problem. Evaluate the limit as x approaches 9, given the function square root x minus 3 over x minus 9. Now, if you're not sure what to do, and if you have a multiple choice test, you could find the value of f of 9.01. So that's close to 9. So let's see what this is equal to. So this is 0.16662. So basically, let's say 0.167. So the answer should be close to this value. And if you want a better answer, plug in 9.001 or even 9.00001. The closer it is to 9, the more accurate the answer will be. But if you have a free response test, then you have to show your work. Whenever you have a square root inside a fraction, what you want to do is you want to multiply the top and the bottom by the conjugate of the numerator. In this case, by the square root of x plus 3 as opposed to minus 3. So don't forget to change the sign. And whatever you do to the top, you must also do to the bottom. Now on the numerator, we're going to FOIL. The square root of x times the square root of x is simply x. And then here we have positive 3 square root x, and then let's multiply negative 3 by root x. So that's negative 3 square root x, and then negative 3 times 3 is negative 9. Now, what I would recommend is not to FOIL these two. Keep it the way it is. It's going to work out nicely if you don't FOIL x minus 9 with the square root of x plus 3. And let's rewrite the limit expression. So now we could cancel positive 3 square root x and negative 3 square root x. 3 plus negative 3 adds up to 0. So what we have left over is x minus 9 divided by x minus 9 times the square root of x plus 3. So notice now that we can cancel x minus 9. So once you get rid of this x minus 9 factor, you can now plug in 9, because this, it prevents us from doing so. It will give us a 0 on the bottom. So once that's gone, now we can use direct substitution with the exact value. So once we plug it in, we don't need to rewrite the limit expression. So all of this is equal to 1 over the square root of 9 plus 3. And the square root of 9 is 3. And 3 plus 3 is 6. So the final answer is 1 over 6. That's the exact answer. Now, 1 over 6 as a decimal is basically 0.166666 repeated. So you can say 0.16, which is basically 0.167. It's close to that. So these two values, they're in harmony with each other. So whenever you're evaluating limits analytically, see if you can either factor, or if you have a complex fraction, multiply the top and the bottom by the common denominator. Or if you have a fraction with a square root symbol inside of it, multiply the top and the bottom by the conjugate of the square root factor. Now the next thing that you need to be able to do is you need to know how to evaluate a limit graphically. So let's say if you want to find these four things. What is the limit as x approaches negative 3 from the left side? So that's a one-sided limit. And what is the limit as x approaches negative 3 from the right side? The right side is indicated by the positive superscript. And what is the limit as x approaches negative 3 from either side? And finally, what's the value of f of negative 3? So these are common questions that you might see in a test when evaluating. I lost my the cat caught my tongue. When evaluating limits graphically. So what is the value that f of x approaches as x approaches negative 3 from the left? So first, identify the value where x is negative 3. So that's this point here. Now, if we follow the function from the left as we approach an x value of negative 3, we're going to be on this curve. So we're approaching negative 3, and notice that the y value there is 1. So therefore, as x approaches negative 3 from the left side, f of x approaches 1. Now what about from the right side? So anywhere along this vertical line, x is negative 3. So we're going to approach that x value starting from the right side. And so it's going to take us to this vicinity where the y value is 2. So as x approaches negative 3 from the right side, f of x is equal to 2. Now what about the limit as x approaches negative 3 from either side? If the left side and the right side, if they differ, then here's something important that you need to know. The limit does not exist. Unless these two match, the limit will not exist. Now what about the last one? What is the value of f of negative 3? So when x is exactly negative 3, what is the function value? So in this case, you need to look for the closed circle at an x value of -3. And basically, that closed circle has a value of -1 on the y-axis. So f of -3 is equal to -1. Now, whenever the limit doesn't exist, you have a certain type of discontinuity. This particular discontinuity is known as a jump discontinuity because there's a disconnect in the graph. A jump discontinuity is also known as a non-removable discontinuity. So let me give you some more questions relating to this topic. So what is the limit as x approaches -1 from the left side? And what is the limit as x approaches -1 from the right side? Now, once you find those two values, I want you to find the limit as x approaches -1 from either side, and then find a value of f of -1. So anywhere along this vertical line, x is equal to -1. So as we approach an x value of -1 from the left side, notice that the y value approaches -3. Now, as we approach it from the right side, the y value is still -3. So notice that the left side and the right side have the same value. Therefore, the limit exists, and it's equal to -3. Now, what about f of -1? So along this line, you want to look for the closed circle, and here it is. And it has a y value of -2. So f of -1 is -2. Now, this type of continuity, or rather discontinuity, where the limit exists, but it doesn't equal to the function value, is known as a hole. And that type of discontinuity is known as a removable discontinuity. So that's simply a hole. Now let's talk about another problem. What is the limit as x approaches -2 from the left side? And also, what's the limit as x approaches -2 from the right side? And also from either side? And finally, what's f of -2? So as x approaches -2 from the left side, so here's where x is -2. As we approach from the left side, notice that the graph goes higher and higher and higher. So therefore, it approaches positive infinity. Now, as we approach -2 from the right side, notice that it goes down towards negative infinity. And these two, they don't match. So therefore, the limit doesn't exist. Some teachers will also say that infinity, because it's not a specific number, they will define it as the limit not existent too. So just keep that in mind. Now, what about f of -2? Now, there's no closed circle along that vertical line, so therefore, this value does not exist either. You could say it's undefined, because typically, whenever you have, let's say if you were to graph 1 over x minus 2, you're going to see a vertical asymptote at x minus 2. And at 2, if you plug it in, you would say it's undefined, because f of 2 will equal 1 over 0. So whenever the function doesn't exist due to a vertical line, you could also say that it's undefined, because that's why you have a vertical asymptote, typically because there's a 0 in the denominator. So just keep that in mind. Now let's try one more set of problems. What is the limit as x approaches 1 from the left, 1 from the right, 1 from either side, and also let's find the value of f of 1. By the way, you need to know what type of discontinuity this represents. That's known as an infinite discontinuity, and it's also a non-removable discontinuity. Now let's move on to the next problem. As x approaches 1 from the left side, notice that the y value approaches 1. And as x approaches 1 from the right side, the y value is still negative 1. So because these two are the same, as x approaches 1 from either side, it's going to be negative 1. The limit exists. Now, f of 1 is also negative 1 because we have a closed circle at this point. Even if there were no closed circle, if there was a straight line, if we didn't have an open circle, it would still be negative 1. Now, whenever all four of these values match up, the function is continuous at x equals 1. Whenever there's a mismatch, it's discontinuous. Either it could be a hole, it could be an infinite discontinuity, or it could be a jump discontinuity. But when all four of these values match, then we can say that the function is continuous at x equals 1. Something else that you'll see in calc are piecewise functions. So this is basically a function that is broken into pieces or different parts. So the function is going to equal 5x plus 3 only when x is less than 1. And it's going to equal x squared plus 7 when x is equal to or greater than 1 but less than 2. And it's going to equal 3x minus 1 when x is equal to or greater than 2. So what I want you to do is identify any points of discontinuity or tell me when it's continuous using limits. Now, if there are no fractions, the only places where it could be discontinuous is at 1 or at 2. But keep in mind, if you do have a fraction, let's say 1 over x minus 4, you can't have a 0 in the bottom of a fraction. So therefore, you know that it's going to be discontinuous at 4. At 4, you're going to have a vertical asymptote, which is going to be an infinite discontinuity or a non-removable discontinuity. So if you see any fractions, look out for when the denominator is equal to 0. If you don't see fractions and you have a piecewise function, in this example, the only place it can be discontinuous is at 1 or 2. For any linear function or quadratic function or any type of polynomial function, it's typically continuous everywhere else. But for a piecewise function, it can be discontinuous at these points, 1 and 2. So how do we tell if it's going to be continuous or discontinuous at those points? Well, let's start with 1. What is the limit as x approaches 1 from the left side? Now, which part of the function will you use? 5x plus 3, x squared plus 7, or 3x minus 1? Now, we're dealing with the left side of 1. So that's when x is less than 1. So it has to be 5x plus 3. So let's replace x with 1. So therefore, the limit is going to approach 8. Now, what about the limit as x approaches 1 from the right side? So this is greater than 1, like 1.01 or something. Therefore, we need to use x squared plus 7 because it's greater than 1 but less than 2. So it's going to be 1 squared plus 7, which is 8. Notice that these two values match. Whenever that happens, for the most part, it's going to be continuous. So therefore, the limit as x approaches 1 from either side is equal to 8. Now you also want to find the value of f of 1. When x is exactly 1, what is the function value? Should we use 5x plus 3 or x squared plus 7? Now we need to use x squared plus 7 because that's when x is equal to 1. But it's going to give us the same value. It's going to be 1 squared plus 7, which is 8. So whenever these four values match, the function is continuous at x equals 1. Now there's something called the three-step continuity test, and it's useful whenever you want to prove if a function is continuous or discontinuous at a certain point. So it's basically what we just did, but in a certain defined order. So here's the three-step continuity test. Step 1, you want to make sure that the function is defined. So you want to make sure that f of a exists. A is basically the x value. And we did that. We said that f of 1 is equal to 8. The second step is that you want to prove that the limit as x approaches a from the left side is equal to the limit as x approaches a from the right side. So basically, you're trying to prove that the limit exists. And it's only going to exist if the left side and the right side matches up. And we did that in this example. We said that the limit as x approaches 1 from the left is equal to 8, which is equal to the limit as x approaches 1 from the right. Now the third step is to basically make a statement. You want to state that the limit as x approaches 1 from either side, which will be equal to these two values, is equal to f of 1, which they will both equal to 8. But this is the three-step continuity test if you want to prove a function is continuous or discontinuous. If all three steps are met, or rather if the criteria of all three steps are met, then it's continuous. If one of these steps fail, it's discontinuous at that point. So let's see if it's going to be continuous or discontinuous at x equals 2. And let's use the three-step continuity test. This time we're going to do it in order. So first, let's make sure the function is defined at 2. So what is f of 2? X is equal to 2 in the third part of the function, 3x minus 1. So it's going to be 3 times 2 minus 1, which is 6 minus 1, and that's equal to 5. So f of 2 is defined. Now, let's make sure that the left-sided limit and the right side are the same. So let's find the value of the limit as x approaches 2 from the left side. So that's when x is less than 2. So we're going to use x squared plus 7. So that's 2 squared plus 7. 2 squared is 4. 4 plus 7 is 11. Now let's check the right side. The limit as x approaches 2 from the right. So that's going to be using 3x minus 1 again. So we know that's going to equal 5. So notice that the left side and the right side doesn't match. So therefore the limit doesn't exist, which means it's discontinuous. The second step failed. Now here's a question for you. What type of discontinuity do we have? If you were to graph it, what would it look like? Whenever the first step succeeds, and if the second step fails, or actually whenever the second step fails, and you don't have an infinity symbol, this is going to be a jump discontinuity. We've covered this earlier in the video. So basically the graph will look something like this. So at x equals 2, we're going to have a y value of 5 and also 11. Now, will both of these be an open circle or will there be a closed circle at one of these points? And which one? So notice that f of 2 is defined. And it's defined here when x is equal to or greater than 2. So therefore, and that's associated with a y value of 5. So this one should be a closed circle. The other one at 11 is an open circle, because this one gave us a value of 11 when x is 2, and x is only less than 2 but not equal to 2. So that has to be an open circle. Now to get the shape of the graph, you need to be familiar with the parent functions. 3x minus 1 is a linear function, and that occurs when x is greater than 2, so it should be going this way with a slope of 3. X squared plus 7, it's a quadratic function with the shape of a parabola, and that's when x is less than 2. So it's going to start at 7 and then go up. And then the left side is going to be, it can be something like this if you don't take into account that function. But if we do, let's see, at 1, this is going to be 8. So let's put 8 here. And that's going to be an open circle at 8 with a slope of 5, but it starts at 3. So this is the first part of the piecewise function. That's 5x plus 3. And then between 1 and 2, we have x squared plus 7. X squared looks like this. So we only need basically this portion of the graph. So this should be somewhat curved. And also we have a closed circle at 8, because f of 1 is equal to 8. So that's how you can graph that particular piecewise function. That's a rough sketch of it. But as you can see, we do have the jump discontinuity. The graph disconnects. Now you need to be familiar with parent functions. You need to know how to graph certain functions in calc. So I'm going to take a few minutes to review that. So the first one, y is equal to x, or x to the first power. That's basically a linear function. It's a straight line. So 5x plus 3, 4x minus 7, these are all linear functions. The next one is x squared. This is a parabolic function. It has the shape of a parabola. It's also known as a quadratic function too. And it basically has a U shape. The next one you need to be familiar with is x cubed. So the parent function looks like this. It's an odd function. This one is an even function. There's symmetry along the y-axis. Whenever you have symmetry at the origin, it's an odd function. The next one you need to know is the square root of x, which has a shape that looks like that. And then there's 1 over x, which is an odd function. It has a horizontal asymptote of y equals 0 and a vertical asymptote of x equals 0. 1 over x squared is going to be an even function. The asymptotes are the same. Next, we have e to the x, which is an exponential function. It increases at an increasing rate. And then there's ln x, which is the inverse of an exponential function. So a logarithmic function increases at a decreasing rate. And then we have the cube root of x, which is an odd function. There's symmetry about the origin. And then also the absolute value of x, which is an even function. There's symmetry about the y-axis. I need to draw that better. So basically it's a V shape. Now don't forget about your sinusoidal functions that you learn in trig. Sine x and cosine x. Sine x starts at the center, and if it's positive sine x, it's going to go up, and then down, and it's going to repeat the cycle. Negative sine x, it starts at the center, but instead of going up, it's going to go down first. If you put a negative in front of a function, it reflects over the x-axis. Positive cosine x starts at the top, and then it alternates. Negative cosine x starts at the bottom, and then it alternates. So that's just a basic review of parent functions that you need to know for your calculus course. Now, I've spent a lot of time on limits because at the beginning of your calculus course, that's what you're going to be doing, mostly limits. But now I want to give you a brief overview of derivatives and integration. And you need to know how to connect derivatives with limits. So what exactly is a derivative? A derivative is a function. It's a function that tells you the slope of the tangent line at any x value. But before I go deep into that, let me tell you how to calculate the derivative using the power rule. So let's say if the function is x cubed, the derivative, also known as f prime of x, sometimes you'll see it written as dy over dx, the derivative is 3x squared. If f of x is x to the fourth, the derivative is going to be 4x cubed. If it's x to the fifth, it's going to be 5x to the fourth. Do you see a pattern? So if it's x to the n, it's nx to the n minus 1. So knowing that, go ahead and find the derivative of these functions. So the derivative of x to the 6th is 6x to the 5th. The derivative of x to the 7th is 7x to the 6th. And for x to the 1, it's 1x to the 0. And anything raised to the 0 power is 1, so the derivative of x is simply 1. The derivative of a constant is 0. When you see 5, think of 5x to the 0 because that's equal to 5. And the derivative of x to the 0 is like 0x to the negative 1, which if you multiply anything by 0, the whole thing is 0. So the derivative of any constant is always 0. Now sometimes you may have a coefficient in front of these values. So let's say if f of x is 4x to the 7th. What is the value of f prime of x? So what you can do is simply rewrite the constant 4 and then differentiate or find the derivative of x to the 7th. So we know that's going to be 7x to the 6th. And 4 times 7 is 28. So the whole answer is 28x to the 6th. So go ahead and find the derivative of these values. The derivative of x to the 5th is 5x to the 4th. So the derivative of 8x to the 5th is going to be 40x to the 4th. Now the derivative of x to the 4th is 4x cubed. And if we multiply that by 9, that's going to be 36x cubed. The derivative of x is 1, so the derivative of 6x is 6. The derivative of x squared is 2x, or 2x to the first power. And so the derivative of 32x squared is going to be 32 times 2x, which is 64x. And that's a simple way of finding the derivative of monomials. Sometimes you may need to find the derivative of a polynomial function. Try this one, 4x to the third power plus 6x squared minus 5x plus 8. If you see this symbol, it's telling you to differentiate what's inside with respect to x. So the derivative of x cubed, we know it's 3x squared. The derivative of x squared is 2x. The derivative of x is 1, and the derivative of any constant is always 0. So now 4 times 3x squared is 12x squared. 6 times 2x is 12x. And so this is the derivative. So if this function, let's say it's equal to y, this is equal to y prime. So you can describe a derivative function as being y prime, f prime of x, dy dx. These are the most 3 common symbols that you'll see. that describes the derivative of a function, or at least the first derivative. Because you could find a second derivative, you could find a third, and you can keep going until you reach 0. Now what about integration? Integration is basically the reverse process of differentiation. So let's say if we want to find, or if we want to differentiate x cubed, the derivative of x cubed is 3x squared. Now the integration of 3x squared is x cubed. So differentiation and integration, these are opposite processes. So how can we go about turning this answer into that? What steps do we have to take? So here's what you need to do. The first thing you need to do is increase the exponent by 1. So add 1 to it. It's going to be 3 instead of 2. And then whatever number you get here, divide by it. So this will give you the original function x cubed. Now, whenever you have an indefinite integral, it's basically an integral with no numbers here. Sometimes you'll see numbers like it could be a 1 and a 4. Then it becomes a definite integral. But if there's no numbers, always put plus c. Because it could be x cubed plus 5, x cubed plus 8, or just x cubed. You don't know what this constant is going to be. If you were to find the derivative of x cubed, it will give you 3x squared. If this constant was 8, the derivative of 8 will be 0. If it was 5, it will be 0. In the end, you'll still get 3x squared. So we don't know what that constant is, so we just put a general term plus c. So go ahead and integrate these values. So all we're going to do is add 1 to the exponent and then divide by that number. So the antiderivative, or the integral of x to the 4th, is x to the 5th over 5 plus c. For the next one, let's add 1 to 3, so it's going to be 4, and then divide by 4. Now 8 divided by 4 is 2, so the answer is 2x to the 4th plus c. Now for the next example, the exponent is 1. So if we add 1 to it, it's going to be 2, and then divide by that number. So it's 5x squared over 2 plus c. And for the last one, if you're going to integrate a constant, just add an x value to it. Keep in mind, the derivative of 7x is 7. So that's integration, or the process of finding the antiderivative. Now let's talk about derivatives and how to use limits to get it. Now let's say if f of x is x squared. We know that f prime of x using the power rule is 2x. But how can we use limits to show it? You need to use this function, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So before you learn the power rule, you're going to learn how to find the derivative using this equation, or the definition of the derivative. And on the free response test, you just have to know how to do it this way. If it's a multiple choice test, you can use the power rule. So how do we apply this equation? Well, we know that f of x is simply x squared, but what is f of x plus h? To find it, all you need to do is replace x with x plus h. So it becomes x plus h squared instead of x squared. F of x is just x squared. And now you just got to evaluate the limit. So what you can do if you want to is you need to FOIL x plus h times x plus h. But for now, I'm just going to rewrite it. So this is x plus h times x plus h minus x squared. Our goal is to get 2x. So now let's FOIL. So first we have x times x, which is x squared. And then we have x times h, and then h times x. So that's going to be xh plus another xh, which is 2xh. And then h times h is h squared. And let's not forget about the negative x squared that we have on the right side. Positive x squared plus negative x squared adds up to 0. And 0 is nothing, so those two will cancel. And so we're left with 2xh plus h squared divided by h. So what do you think we need to do next at this point? At this point, we need to take out an h. If we do so, it's going to be 2x plus h. And notice that we can cancel the h on the bottom. Once that h disappears, we can now plug in 0. Before we can't, because we'll get a 0 on the bottom. And so now what we have left over is the limit as h approaches 0, 2x plus h. Now we need to rewrite the limit until we substitute h with 0, which we can now do. So it's going to be 2x plus 0, which is 2x. And as you can see, these two answers, they match. So that's how you can use limits to find the derivative of a function. Now let's say if f of x is equal to x cubed. Using the power rule, what's f prime of x? We know that f prime of x is 3x squared. Now let's talk about what the derivative means. We said that the derivative is a function that tells us the slope of the tangent line. So as we can see, we have a function and it's based on x. So the slope of the tangent line will change for different values of x. Now if we were to graph x cubed, I'm just going to focus on the right side of x cubed. It's going to look like this. And let's say at this value, x is equal to 1. What is the slope of the tangent line when x is 1? To find it, all you need to do is plug in 1 into the derivative. So f prime of 1 is equal to 3. So keep in mind, 3x squared is the derivative of a function. It's a function based on x or some other variable. F prime of 1, which is 3, that's a number. That's the slope of the tangent line. So the slope of the tangent line is a number, the derivative is a function. But you can use the derivative to find the slope of the tangent line at any value of x. So at x equal 1, the slope of the tangent line should be 3. A tangent line is basically a line that touches the curve at only one point. So notice that it touches it only at the blue point. My drawing is not perfect, so hopefully you understand. So that's the tangent line. And at 1, the slope is 3. Now the slope, let's say at 0.5, is different. It's going to be much less than 3. So as you can see, the slope changes because we don't have a straight line. We have a curve that's not straight. And so the slope will constantly change. Now it turns out that there's another way to approximate the slope of the tangent line. And you can do so by finding the slope of a secant line. A secant line is a line that touches the curve at 2 points. So let's say these 2 points. If we draw a line between those 2 points, it's going to look like this. So notice that those 2 lines, the secant line, which I'm going to write S to represent secant, and the tangent line, they're almost parallel to each other. So if you choose 2 points that are very close to the tangent line, or the point of tangency, which is x equals 1, the slope of the secant line will approach the slope of the tangent line. I may need to draw a bigger picture. So let's say here is the point of tangency, and that's the tangent line, which I missed the point. if I choose these 2 points to be the points of my secant line, as you can see, these 2 lines are not really parallel, so the slopes will differ. But if I choose 2 points that is very close to the point of tangency, which is at x equals 1, then the slope of the secant line, I can use that to approximate the slope of the tangent line, which is what I want to do in this example. So how can we find the slope of the secant line? How can we calculate it? In algebra, you've seen this equation. Slope is equal to y2 minus y1 divided by x2 minus x1. In calculus, it represents the average rate of change. That's the slope of the secant line. So I'm going to put ms for slope of the secant line. And that's equal to f of b minus f of a over b minus a, where a is the first x value, b is the second. So with regard to the blue point, this is a and this is b. So let's see if we can estimate the slope of the tangent line using the slope of the secant line. The slope of the tangent line in our example is equal to 3. It's basically this number right here. So now we need to choose 2 points, and you want one to be the center. As you can see, the point of tangency is in between A and B. So pick 2 numbers where 1 is the midpoint of those 2 numbers. So let's try 0 and 2. So this is A, this is B. And let's calculate the average rate of change. Now remember these terms. The average rate of change is the slope of the secant line. The instantaneous rate of change is the slope of the tangent line. So if you get a question to ask you to find the instantaneous rate of change, find the first derivative, plug in your x value, and here it is. So 3 is the instantaneous rate of change, which is the slope of the tangent line. Now if you want to find the average rate of change, it's going to be f of b minus f of a over b minus a. So in this case, it's going to be f of 2 minus f of 0 over 2 minus 0. So it's the change in the y values divided by the change in the x values. So f of 2, we got to plug it into this equation. That's going to be 2 to the third power. And then f of 0 is just 0 to the third over 2 minus 0. 2 to the third is 8. So 8 over 2 is 4. So 4 is close to 3, but it's not exactly 3. So as you can see, 0 and 2, they're pretty far apart from 1. And so that's why these 2 values are not very close to each other. So let's see if we can pick something else. But I'm going to keep the answer here. So the slope of the secant line, or the average rate of change, is 4 when a is 0 and when b is 2. Now pick 2 numbers where 1 is the midpoint, but the 2 numbers are very close to 1. So let's use 0.9 and 1.1. They're a lot closer to 1, but 1 is still in between those 2 points. And let's see what the slope of the secant line is going to be this time. So it's going to be f of 1.1 minus f of 0.9 divided by 1.1 minus 0.9. So this is going to be 1.1 to the third power minus 0.9 to the third power. 1.1 minus 0.9 is 0.2, so let's just put that here for now. Now 1.1 to the third power minus 0.9 to the third power is 0.602. And if we divide that by 0.2, this will give us 3.01. So that's the slope of the secant line. Now let's look at these 2 values. So when we chose 2 points that were pretty far away from 1, like we did here, the slope of the secant line and the slope of the tangent line, they differed significantly. However, when we choose 2 points that is a lot closer to 1, like these 2 yellow points here, the slope of the secant line became a better approximation of the slope of the tangent line. 3.01 and 3, they're very close to each other. So the slope of the secant line can be approximated to the slope of the tangent line whenever the change in x values, if it becomes very small, if it approaches 0. As we saw, when a was 0 and b was 2, the change was relatively large, and the approximation wasn't that good. However, when a was 0.9 and when b was 1.1, the change in x was small, and so the slope of the secant line was approximately the same as the slope of the tangent line. So therefore, as the difference between a and b gets smaller and smaller and smaller, then we could say that the slope of the secant line becomes the slope of the tangent line. Keep in mind, the difference between b and a is delta x. Delta x means the change in x values. So here, delta x is 2, and here the change in x values is 0.2. So 0.2 is a lot closer to 0 than 2, and that's why this gave us a better approximation of the slope of the tangent line. Now the slope of the secant line, we said, is the change in y values divided by the change in x values. The slope of the tangent line is basically the derivative at a certain value. So keep in mind, f prime of x is the derivative of a function, and f prime of a is the slope of the tangent line because you're plugging in a number to get a number. Now, delta y is y2 minus y1. Delta x is x2 minus x1. And as these two values approach 0, or as the difference approaches 0, then this is going to equal to f prime of a. So therefore, we need to write a limit expression. So the limit as delta x approaches 0, so let's call this delta x, then the slope of the secant line will become equal to the slope of the tangent line, which is f prime of a. Now there's a formula that's similar to the expression that we just wrote. It's known as the alternate form of the derivative, or the definition of the derivative. And here it is, f prime of a, that is the slope of the tangent line, or the instantaneous rate of change of the function, that's equal to f of x minus f of a over x minus a. So notice the similarities between this expression and what we have here. F of x is a y value. So f of x minus f of a is the difference in y values, and x minus a is the difference in x values. And there's something I'm forgetting to write. I need to write the limit expression. So here's the whole equation. F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. So this is the entire equation that will help you to find the slope of the tangent line, or the instantaneous rate of change using limits. Now let's say that f of x is x cubed again. Go ahead and find f prime of 3. So find the instantaneous rate of change of the function at 3. Now let's do it the easy way first. So let's find the derivative of the function. The derivative is 3x squared. Now to find f prime of 3, we just got to plug in 3 into this expression. So that's going to be 3 times 3 squared. And so the instantaneous rate of change, which is the slope of the tangent line, that's equal to 27 in this example. Now let's get this same answer using limits. So let's use this formula. F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. So in this example, a is 3. So we're looking for f prime of 3. So therefore, that's equal to the limit as x approaches 3 of f of x minus f of a, or f of 3. So everywhere you see a, replace it with 3 over x minus 3. Now f of x is equal to x cubed in our example. And f of 3, we can find it by plugging in 3 into that equation. So that's going to be 3 to the third power, which is 27. Now, how can we evaluate this limit? What is the limit as x approaches 3 of x cubed minus 27 over x minus 3? It turns out that we could factor the expression. But let me get rid of some stuff first. To factor it, we need to use the difference of perfect cubes formula. And here it is. A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So therefore, we have the expression, the limit as x approaches 3, it's going to be a minus b, which is x minus 3, times a squared, or x squared, plus ab, so that's going to be plus 3x, and plus b squared, or 3 squared, which is 9. So now we could cancel x minus 3. Now that this factor is gone, we can plug in 3 into the surviving function. So we have the limit as x approaches 3 of x squared plus 3x plus 9. So that's 3 squared plus 3 times 3 plus 9. 3 squared is 9, 3 times 3 is 9. So adding 9 3 times is the same as multiplying 9 by 3, which is 27. So notice that we get the same answer. So that function gave us the slope of the tangent line, or the instantaneous rate of change at 3. Now, it's important for you to understand the meaning of this stuff, so let's summarize what we've just learned. Let's say f of x is x to the fourth. That means the first derivative is 4x cubed. And the instantaneous rate of change, let's say at 2, that's going to be 4 times 2 to the third, which 2 to the third is 8, so 4 times 8 is 32. Now, this function, or this equation, the definition of the derivative, this will give you a function in terms of x. So this gives you the derivative, which is going to be 4x cubed. So anytime you use this function, you're going to get a derivative in terms of x, or a function in terms of x. Now the alternative form of the derivative will give you a number. So that's f prime of a. So that's the limit as x approaches a of f of x minus f of a over x minus a. In this example, it's going to give you the number 32. So a is 2. So whatever number you see inside here, that's your a value. So make sure you understand this. This function gives you the derivative, which is a function that helps you to find the slope of the tangent line. And so this is the derivative. It's a function based on x. This equation will give you the slope of the tangent line, which is 32. And that's the same as the instantaneous rate of change. And finally, if you want to find the average rate of change, that's the slope of the secant line, and that's equal to f of b minus f of a over b minus a. Now sometimes you may not have a function, and the only way to estimate the slope of the tangent line is to use the slope of the secant line. It's particularly useful if you're given a data table and you want to find the instantaneous rate of change. So you can estimate it using the slope of the secant line, which is the average rate of change. So make sure you remember that the average rate of change is the slope of the secant line, and the instantaneous rate of change is the slope of the tangent line. And you can find the slope of the tangent line by finding the first derivative and plugging in the x value. Now, let's talk about position, velocity, and acceleration. S of t is the position function. It tells you where a particle or an object is located. It could be on the x-axis or on the y-axis. but for the most part, I'm going to refer to the x-axis. So s of t is the position function. V of t is the velocity function. Velocity tells you how fast an object is moving, and it also tells you the direction. So if the velocity is positive, that means that the object or the particle is moving to the right. If the velocity is negative, then the object is moving to the left. And if the velocity is 0, it can mean one of two things. The object could be at rest, or it could be temporarily at rest and change in direction. So if they ask you when is the particle's change in direction, you need to set the velocity equal to 0 and find t. A of t is the acceleration. The acceleration tells you how fast the velocity is changing. So for example, an acceleration of 5 meters per second squared tells you that the velocity is increasing 5 meters per second every second. So if you make a table between time and velocity, and let's say at t equals 0, the velocity is 0. 1 second later, the velocity will be 5. 2 seconds later, 10. 3 seconds later, 15. So acceleration tells you how fast the velocity is changing. Whenever the acceleration is positive, the velocity is increasing. And whenever the acceleration is negative, the velocity is decreasing. So these are some notes that you want to take. Now you need to know how speed is related to velocity and how it's different. Speed is basically the absolute value of velocity. Speed is a scalar quantity, velocity is a vector quantity. Velocity has magnitude and direction, speed only has magnitude. So for example, let's say if an object is moving 30 meters per second east. The 30 meters per second describes the speed of the object, but the 30 meters per second with the direction east tells you the velocity. So in this case, the velocity is positive 30 and the speed is positive 30. Now let's say if the object is moving at 25 meters per second west. The speed is always positive, it's positive 25. The velocity is negative 25 because the object is moving in the negative x direction. So velocity can be positive or negative. Speed is always positive. So the direction like west, east, north, south, it's not relevant to speed. But it is relevant to velocity. So that's it. Velocity is just speed with direction. Speed is always positive. Velocity can be negative or positive. Now you need to know how to tell if a particle is speeding up or if it's slowing down. And there's a simple way to do that. The particle is speeding up anytime the velocity and the acceleration share the same sign. It's slowing down when the signs of the velocity and the acceleration are different. So if the velocity is positive and if the acceleration is positive, then the particle is speeding up. Also, if the velocity is negative and if the acceleration is negative, the object is still speeding up. It's just in the negative x direction. Now, it's slowing down when the signs are different. So if the velocity is positive and the acceleration is negative, it's slowing down. So what's happening is, because the velocity is positive, the object is moving to the right. But because the acceleration is negative, the object is slowing down, it's decelerating. Imagine moving to the right but hitting the brakes. Now, the velocity can be negative and the acceleration can be positive. In this case, it's still slowing down. So imagine if the vehicle is moving to the left, but it's accelerating towards the right. Basically, it's moving to the left while hitting the brakes. And that's how it's slowing down. In this case, it's moving to the right and putting on the gas, so it's speeding up to the right. Here, it's moving to the left with the gas pedal being activated, so it's speeding up towards the left. So make sure you understand this. So if the signs are the same, it's speeding up. If the signs are different, then it's slowing down. Now there's some other things you need to know. Let's talk about units. The units of the position function will be things like meters, feet, miles, kilometers. But the most common unit you'll see is probably meters or feet in calculus. The units for velocity or speed, meters per second, feet per second, miles per hour, or kilometers per hour. And the unit for acceleration, meters per second squared, and feet per second squared. We'll use this later on in this video, but I want to just give you this information now, because you need to know how derivatives and integration relate to these variables. The derivative of the position function is equal to the velocity function, and the derivative of the velocity function will give you the acceleration function. The antiderivative of the acceleration function can give you the velocity function, but you need an initial point to find the value of c. This is known as an indefinite integral. However, let's say if you were to have some values here, it becomes a definite integral as opposed to an indefinite integral. And this won't give you the velocity function. Rather, it gives you the change in velocity. Likewise, the indefinite integral of the velocity function can give you the position function if you can find a constant c. The definite integral of the velocity function will give you the displacement, which is the change in position. Displacement and distance is the same if the object moves in one direction without changing direction. If it changes direction, then displacement and distance are different. So this function always gives you the displacement, which sometimes will be equal to the distance depending on the circumstance, but it's always equal to displacement. So for example, let's say if your displacement is 10. This doesn't tell you what the initial position is or what the final position is. It doesn't tell you where you started or where you ended. It simply tells you the change between your initial and final position. It also doesn't tell you how you got from where you started to where you ended. So for example, you could have started at 2 and ended at 12, or you could have started at 4 and ended at 14. All we know is that the change in position is 10. It doesn't tell us where we started if we started at 2 or 4. And it really doesn't tell us where we ended. It could be 12 or 14. Now, if we know we started at 2, then we know that we're going to end at 12 because the change is 10. And so the definite integral of velocity will give you the displacement. It won't tell you where you started or where you ended. It just tells you the change in position. It also doesn't tell you how you got there. For example, you can go from 2 to 12 by going, let's say, 4 units to the right, and then 6 units to the left, and then 12 units to the right. In this case, your displacement is still 10. If you add positive 4, negative 6, and positive 12, you'll get 10. But your distance is not 10. You travel the distance of 4 plus 6 plus 12, or a distance of 22. So this number doesn't tell you how you got from where you started to where you ended. It doesn't tell you the path. It simply tells you the change in position. You could have taken the direct path. You could have went to the right and then went to the left. I mean, there's an infinite number of ways in which you can go from 2 to 12. You could have taken a curved path. The 10 doesn't tell you what path you've taken. It tells you just the change in position. Now, the distance will depend on the path you're taking. If you travel, let's say, 15 units to the right and then 5 units to the left, your distance is 20, but your displacement is positive 10. So keep that in mind. The definite integral of velocity gives you the displacement and not necessarily the distance. Now let's summarize what we've just learned. If you want to go towards the right, you need to find the derivative of the function with respect to time. The derivative of the position function s of t is equal to the velocity function, and the derivative of the velocity function is equal to the acceleration function. Now, if you want to go towards the left, you need to integrate. The integral of the acceleration function can be used to give you the velocity, and the integral of the velocity function can be used to find the position function. So if you differentiate, you're going to go towards the right. If you're integrating, you're going to go towards the left. Now, to help you remember this, the units, you can use the units to figure it out. So let's say if we have a velocity function with respect to time. So let's say we have a velocity time graph. So the velocity is on the y-axis, time is on the x-axis. And let's say the units for velocity is meters per second, and the units for time is seconds. And we have some graph. Now, if we want to find the derivative of the velocity function is equal to the acceleration function. And we could find the derivative, we can use the derivative to find the slope of the tangent line. So therefore, the slope will give us the instantaneous acceleration at some point. And here's how we can show this. We know that the slope is y2 minus y1. So it's the change in y divided by the change in x. So when you're looking for the derivative of something, you're basically dividing the y values by the x values. So the y values have the units meters per second. The x values have the unit seconds. So what we have is meters per second divided by seconds. And if you use the keep, change, flip principle, keep the first fraction the same, change division to multiplication, and flip the second fraction. So instead of s over 1, it's going to be 1 over s. This will give you meters per second squared, which is the unit for acceleration. So as you can see, this tells you that the slope of a velocity time graph can give you the instantaneous acceleration, and the derivative of the velocity function gives you the acceleration function. So make sure you understand that. Now what about the antiderivative of the velocity function? The antiderivative of the velocity function will give us, or can give us, the position function. In addition, if we use a definite integral, this will give us the displacement. So the displacement can be found by finding the area under the curve. And to find the area, you need to multiply the x values by the y values. To find the slope, you need to divide the y values by the x values. So notice the difference. When you're differentiating something, you're dividing the y values by the x values. That'll give you the slope. When you're trying to integrate something, you're really multiplying the x and the y values together. So you're looking for the area under the curve. In this case, the x values has the unit seconds. It's associated with time. The y values has the units meters per second. So if you multiply seconds by meters per second, notice that the unit seconds will cancel, and you're going to get the unit for displacement or position, which is going to be meters. So I want to make sure you understand that. So let's just summarize the difference between differentiation and integration. So differentiation is the process of finding the derivative of something. Let's say the derivative of f of x, which is f prime of x. Integration is the process of finding the antiderivative, which can give you the original function. Now, when you're differentiating, you can use that to find the slope, and that is the slope of the tangent line. When you're integrating, you're actually finding the area under the curve. And when you're finding the slope, you're basically dividing the y values by the x values. So in the case of a velocity function, we're dividing meters per second by seconds. And so the slope of a velocity function is therefore equal to acceleration, because it gave us the unit meters per second squared. So anytime you're differentiating something, you're dividing the y values by the x values. Now, in the case of integration, you're looking for the area, which is basically length times width, x times y. So you could find it by multiplying delta x and delta y. And in the case of a velocity time graph, we're multiplying seconds by meters per second, which gave us the unit meters. And so we could say that the area under the velocity time graph will give us the displacement, the change in position. So make sure you understand that. So the area of a velocity time graph is equal to the displacement, and the slope of a velocity time graph is equal to the acceleration. Now let's see if you understand this. So let's say if we have a position time graph. So I'm going to put S and T. And let's say the units are meters and seconds. Now, what does the area represent? And what is represented by the slope? Let's see if you understand this. So the area, we know it's basically x times y. So in this case, we're multiplying seconds times meters. Meters times seconds is basically nothing. There's nothing significant about it in terms of practical physics and calculus. So there's no point in finding the area of a position time graph. Now, what about the slope? The slope is basically y divided by x, the change in y over change in x. So we're taking the unit for the y values, which is meters, and dividing it by seconds. Notice that this is the unit for velocity. So therefore, the slope of a position time graph is equal to the instantaneous velocity. Now, what about an acceleration time graph, where acceleration has the unit meters per second squared and time has the unit seconds? What does the slope and what does the area represent for an acceleration time graph? Feel free to pause the video. So we know the slope is the change in y over the change in x. So in this case, that's going to be meters per second squared divided by seconds, which will be meters per second cubed. Now, in a typical calculus course, you really don't have to worry about the slope of acceleration. But I remember that one textbook, it defined it as jerk. Don't know why it calls it that, but that's what it defines it at. But in calculus, for the most part, you don't have to worry about the slope of an acceleration, because it's rare that you'll see units like meters per second cubed. However, the area of the acceleration time graph, that's important, that's significant. The area is going to be delta x times delta y. So time is on the x-axis with the unit seconds. Delta y is acceleration with the unit meters per second squared. So basically we have seconds times meters over second squared is seconds times seconds. So we could cancel s, which leaves one s behind. So we get meters over seconds, which is the unit for velocity. So therefore, the area of an acceleration time graph will give you the change in velocity as indicated by the units meters per second. So that's basically it for this video. So now, hopefully you have a better understanding of limits, derivatives, and integration. So thanks for watching. And by the way, for those of you who want to find more of my calculus videos, which can help you later throughout the semester, feel free to visit my channel and look for my calculus playlist. You could also visit my website, video-tutor.net, and you could access some of my playlists at this website too. and don't forget to put www. So feel free to check out that website, and you can find other playlists that I have too on physics, chemistry, algebra, trig, if you need help in those courses as well.